Question 1A. So this question is about the conjugate acid-base pair and the buffer. So it starts with this disodium phosphate and the monosodium phosphate. Okay, so in order to identify the conjugate acid-base pair, it's better for us to focus on the anion, which is the hydrogen phosphate and the dihydrogen phosphate. So if let's say there is an acid solution, the hydrogen phosphate, this one, will gain proton from hydronium and it will form dihydrogen phosphate. So means the hydrogen phosphate is a proton acceptor. Proton acceptor is a base. And of course, hydronium ion now is a proton donor, is acid. After this hydrogen phosphate gains the proton, it will form this dihydrogen phosphate. So the dihydrogen phosphate now is a proton donor because it will donate proton to H2O to form this hydrogen phosphate again. So means the dihydrogen phosphate here is a proton donor, is the acid. So in these two phosphate, we know that the dihydrogen phosphate is the proton donor acid. So means here the acid you should put dihydrogen phosphate, and the base is conjugate base, you should put this hydrogen phosphate. Part 2. Define buffer solution. Okay, this one is very easy. Solution, there are 2 marks here. So the first one is the solution that resists change in pH, 1 mark, when a small amount of acid added. Okay, which means when we add a small amount of acid or alkaline, the pH of the solution will not change much. Part 3. Write 2 equations to show how the mixture of this hydrogen phosphate and dihydrogen phosphate act as a buffer. Okay, again, we try not to use the sodium ion, and we just use the hydrogen phosphate and the dihydrogen phosphate. So when we have these two anion, so we know that this one is acid and this is a base. Okay, this one we already identified just now. Okay, means the acid will react with hydroxide, the base will react with the hydrogen ion. So let's start with this base. So now we know that the hydrogen phosphate is the ones that gains proton because it is a base. So after it gains proton, so it will form this dihydrogen phosphate. So therefore, the hydrogen ion or the acids that added now is gone. Okay, if there is an addition of alkaline, the dihydrogen phosphate, okay, which is the acid now, will try to react with this hydroxide by donating a proton. So this dihydrogen phosphate will donate 1 proton to the hydroxide and it will form H2O. And of course, itself will form the hydrogen phosphate. So this is how the buffer solutions works. And you must put the buffer species. So the buffer species, okay, will be these 2 acid-base pair. Now part 4. Identify 1 inorganic ion that act as a buffer in the blood. So first, you need to know the buffer in the blood is because of the CO2. CO2 dissolve in the this water, so you form the carbonic acid. Carbonic acid will dissociate and form this. So means the buffer system in the blood is the carbonic acid and this hydrogen carbonic. So these 2. And it's asking inorganic ion. So therefore, you must put hydrogen carbonic. Okay, part B. Compound E is the hydroxide of group 2 elements. Compound E is a strong alkaline. Most likely, we know that is barium hydroxide. We still don't know. We need to find it out later. Let's put M for this part. So when this metal hydroxide, group 2 metal hydroxide, is dissociate, so it will form this group 2 ion and 2 moles of hydroxide. Okay, so the mole ratio is 1 to 2 mole. Okay, so later we're going to use this mole ratio. First, part 1 show that the concentration of hydroxide ion in the solution of F is 0.123. So again, compound E dissolve in water to form solution F. And now the concentration of the hydroxide ion in F we can get it from the pH of the solution. Okay, so first you need to know pH is equal to negative log concentration of H+. Okay, so pH is given 13.09. So therefore we will get the concentration of hydrogen ion. So 10 power of negative 13.09. So we will get 8.128 times 10 power negative 14. Okay, so we use the Kw expression. So Kw is equal to the concentration of hydroxide times the concentration of hydrogen ion. Okay, therefore, the concentration of hydroxide is equal to the Kw over the concentration of hydrogen ion. Okay, so by doing this, you will get this. So it's proven. Okay, 0.123 mole per dm cube. Part 2. Explain why the concentration of a compound E in the solution of F is 0.0615. This one is very straightforward. We just need to get from this part again. So because we know that the mole ratio of the metal hydroxide to the hydroxide ion is 1 to 2. So when this is 0.123, so the concentration of the compound E, it should be half. So 0.0615. Okay, this one is very easy. Okay, because 1 mole of E produces 2 moles of hydroxide. Okay, so part 3. Use the concentration given in the part 2, identify compound E. Okay, so first, one very important part is you need to find the mass of the E that dissolve in 1 dm cube. Because in the question, it just given this one, 2.63 gram of E dissolved in 250. So in 1 liter means it's 4 times. So in 1 liter means it's 2.63 times 4. So means it's actually 10.52 gram in 1 liter. Okay, once you get this mass, so you can use you can get the molar mass. So molar mass is this 171.1. Okay, you just need to use 10.52 over the 0.0615. Okay, that's given. Because both already in dm cube, so you can use this 0.0615 mole per dm cube. So this is mass per dm cube, this is mole per dm cube. So therefore, it's the mass over mole, you get the molar mass. So which is 171.1. Okay, so this one's still not the answer. Okay, because we know that the mass of the hydroxide, it will be 17 times 2. Right. So the metal, group 2 metal plus 34 equal to this molar mass. Okay, so the group 2 metals is 137.1, okay, which is barium. So it's confirmed barium. Okay, compound E, therefore we know that is barium hydroxide. Part C. Compound E is much soluble than magnesium hydroxide. A saturated solution of magnesium hydroxide in the water has a concentration of 1.4 times 10 to the negative 4. calculate the solubility products, KSP, of the magnesium hydroxide, including units. First step you need to do is this one. Try to give an equation. So equilibrium between this magnesium hydroxide and this magnesium ion and hydroxide. So when X mole of this magnesium hydroxide dissolve, it will form X mole of magnesium ion and 2X mole of this hydroxide. So this is the unknowns that you should put, right? But you no need to find this unknown because already given. So the X now is the one that given, 1.4 times 10^84. The hydroxide is double, so it's 2.8 times 10^84. Okay, so substitute these two concentration to the KSP expression. So KSP is equal to the concentration of magnesium ion times the concentration of hydroxide squared. Okay, so you substitute these two concentration in this KSP, so you get 1.1 times 10^11. So the units will be this mole per dm cube. Okay, so is bracket, so is power 3. So at the end you get this mole cube dm -9. Okay, part D. Explain why compound E is much soluble than magnesium hydroxide. Compound E already identified is a barium hydroxide. So why barium hydroxide is more soluble than magnesium hydroxide? So this is the answer in the mark scheme. So I'll just tell you roughly how we get it. So because it's a comparison between the magnesium hydroxide and barium hydroxide. So actually we should use this one to compare. So we have this equation. The delta H solution is equal to the delta H hydration minus the lattice energy. So this is equations that we should use because we know that we should know when the delta H solution is more negative or more exo, so the salt is more soluble. So let's check the delta H solution for both hydroxide. Magnesium hydroxide, the actual hydration's enthalpy is this. So it's negative 2811. And the lattice energy is negative 3087. So if we combine these two, so we get 276 kilojoule per mole. Okay, so this is the actual value for this hydration enthalpy and lattice energy. Again, hydration enthalpy for the magnesium ion and the hydroxide together. And this is the lattice energies of the magnesium hydroxide. So when you combine this, you get 276. So it's positive. For this barium hydroxide, okay, so the hydration enthalpy is for this barium hydroxide is negative 2048, and the lattice energy is negative 2053. So if you combine this, so you get 5. So it's still positive, but we know that the delta H solution for the magnesium hydroxide is more endo than the barium hydroxide. Barium hydroxide is more exo, is more soluble. Okay, so why this barium hydroxide is more soluble? Because there is a change. Okay, as you can see, the hydration enthalpy when down the group is become less exo, you see. For this hydration enthalpy of this magnesium hydroxide, so is more exo, and the barium hydroxide is less exo. Means when down the group, we know that it's become less exo. For the lattice energy also, both become less exo. Means that this one is to this, it become less exo. But there is a difference. We know that from here, the lattice energy is changed more. So the values here is larger. So that's why in the mark scheme, you see is change more, because this one is change faster. Okay, again, both hydration enthalpy and lattice energy, they become less exo. So from this value you can see the hydration enthalpy is changed lesser and the lattice energy it changed more. Okay, because of this, at the end, the delta H solution for barium is more exo, so it's more soluble. There is a reason why this lattice energy it changed more. Just because the size of the cation. The size of cation means the group 2 cation with the hydroxide, they are comparable. So the hydroxide, the size is not really that large. So the lattice energy is affects greatly by the cation size. So therefore, when down the group, the lattice energy it change more than the hydration enthalpy. That's the theory behind that, right? So that this is the answer in the mark scheme, no much different. So you just you can actually get from that. Down the group, the lattice energy and the hydration's enthalpy both become less exo, as I told you just now. Okay, it's just because of the lattice energy change more than hydration enthalpy, like I told you just now. At the end, the delta solution, enthalpy change of the solution for barium hydroxide is become more exothermic, means more soluble. Okay, that's all. Thank you.